Welcome back. Let's take some of these concepts we've been talking about and work on applying them. So right here we have a reaction between cobalt chloride and sodium hydroxide, and we want to write a balanced molecular equation for that. And so we want to figure out, are we going to form a precipitate? Well, we talked about hydroxide ions. Hydroxides are generally insoluble, so that means that our hydroxide can react with the cobalt ions here to form the compound cobalt. My handwriting is not the best, but we'll just have to roll with it. Cobalt hydroxide. And that would be a solid. That's going to be insoluble. Now, so we're going to form that cobalt hydroxide. You might be wondering, how did we know that there's going to be two hydroxides for that cobalt? Well, cobalt here has a 2+ charge because the charge of an ionic compound has to always sum to 0. And so if each of our chlorides is 1 minus, then what that means is that our cobalt must be 2 plus in order for those charges to cancel. And our hydroxides are 1 minus, sodium's 1 plus, and so it would take 2 hydroxides to cancel out the charge on that 1 cobalt. So how do we know that chloride's 1 minus and sodium's 1 plus? We can tell that based on periodic table position. So sodium, well, if you haven't learned that already, you'll be learning more about it, but sodium along with group 1A metals forms a +1 charge. Group 7A elements form a 1 minus charge. Cobalt's unpredictable. It's a transition metal, so we have to figure out cobalt based upon the chlorides. And then hydroxide's a polyatomic ion. It's a common one, so you're going to want to memorize that if you haven't already. So memorize the names, formulae, and charges of those common polyatomic ions. So what that means in order to balance this is we'd actually require 2 of these sodium hydroxides here to give us those 2 hydroxides. And our other product here would be 2 NaCl, and this would be aqueous. And so why 2 NaCl? Well, we are looking for the smallest ratio that gives equal amounts of positive and negative charge. That'd be 1 sodium plus 1 chloride. We have 2 of those ions, so we need that 2 out in front. And this would be aqueous because our rules told us that essentially all sodium compounds, ionic compounds, will be soluble. So there is our molecular equation. Let's take a look at how we did. Bam! Looks like we did well. We got it correct. And their version's much neater than mine. My apologies about my handwriting on the computer here. I'm working on it. So from there, what you might be asked to do is write both a total ionic and a net ionic equation. So what we do to show the total ionic is we take anything that's aqueous. So that includes our cobalt 2 chloride, our sodium hydroxide, and our sodium chloride, and we're going to show those as being dissociated. So don't forget to show the charges on these, and remember the the polyatomic ions stay together, so our O and H don't break apart, it stays as OH. And again, we've shown states for all of these right here. You might be wondering, well, why isn't this cobalt hydroxide shown as being dissociated? Well, it's because it's a solid, and things that are solid aren't dissolved, therefore they won't be shown as dissociated. It's an important note right there about the ionic equations. And so let's take a look at our spectator ions. Looks like we have 2 sodiums before, 2 sodiums afterwards. They don't actually participate. We have 2 chlorides before, 2 chlorides after, so we're going to leave those out of our net ionic equation, and boom, here we show just the ions that actually actively participate in the reaction. So here is our net ionic equation. Spectators left out, all states are included. Alright, so now that we've talked about some concepts, let's talk about some actual practices we'll be utilizing in this lab. So in this lab, we're going to be measuring out 1 milliliter of a bunch of different things, but the problem is there's no need to waste all that time of measuring and cleaning and measuring and cleaning and measuring and cleaning with your test tube, or excuse me, with your graduated cylinder or whatever other measuring tool you might use. There's a trick we're going to employ to save time here. And the first thing I want to talk about is always label your chemicals. So use pens and tape to label your test tubes, label your beakers, label everything, your Erlenmeyer flasks, anything that might have chemicals in it. And this is very important because not only is it a legality thing and a safety thing because it prevents accidents, but it's also a convenience thing because most of our chemicals look like clear liquids or white powders and we can mix them up very easily. And this is definitely a lab where it'd be easy to mix up your chemicals. And then you can fail the lab because you didn't have the data you needed or the experiment didn't work or things like that. So label, label, label. Trust me, it'll save you time. All right, so how else are we going to save time? Well, in order to avoid doing that repeated 1 milliliter measurement over and over, you want to collect a bunch of test tubes. And these are all about the same size and shape. So what you want to do is take your test tubes, and I'm going to drop some kind of crappy tape on them and use some tape to mark the lower portion of them. And so these are all about the same size and shape, these almost identical test tubes. So what you want to do is take your graduated cylinder and or whatever measurement device that the lab implies, and you want to measure out 1 milliliter of water and add that in. And you want to mark the tape to show that 1 milliliter mark on that test tube. And then you're going to add another milliliter and you're going to make another mark on that tape. So now you have a 1 and 2 milliliter mark on your test tube. It's going to be able to give you some pretty decent rough measurements, good enough for our purposes, about what 1 milliliter and what 2 milliliters looks like in these test tubes. And let's see if I can draw this well. It's a little hard with the mouse, but what you want to do is take all these other test tubes that have already been marked with tape and whoop, just kind of draw a line across. So you mark all of them for that 1 milliliter. And so now you can just fill them up to that first mark on the tape to mark the 1 milliliter of material being added. And that's going to save you a lot of time in your measurements. And then we're going to do the same thing. Let's see if I can draw another straight line. Can I do it? Looks like it worked. Good enough. So then we have in all of them marked a 2 milliliter line. So if we look at our tape here, we have a 1 mil and a 2 milliliter marking. And that's going to save you a ton of time during your lab because now you don't need to use the graduated cylinder over and over. So just measure these once, make those markings on those test tubes, and then you'll have, on the tape on those test tubes, then you'll save yourself a lot of time. All right, so another important skill from this lab and practice from this lab is that sometimes it can be kind of hard to see precipitates. Now sometimes it's going to be incredibly easy and your solution is just going to look like a bunch of milk, and you know the precipitate's going to be super obvious, it's going to fall to the bottom or it's going to look super milky. But other times it might be kind of faint, so we can use the Tyndall scattering or Tyndall effect to identify if we have a precipitate present. So we have here 2 containers of fluid. They look quite similar to the naked eye. But notice they look very different once we actually shine this bright light on them. So right here we have a solution with no precipitate. And the one with no precipitate, the light passes right through. But for this one right here, you notice it looks sort of foggy. When that light hits the fluid here, we see the scattering of the light. And so that means that it's faint. It's a little hard to see with the naked eye, but with that bright light, we can clearly see the light scattering off the precipitate particles, the very tiny precipitate particles. So you might have some mixtures that are unclear in this lab, and so we'll have a similar lamp to the one shown in the photo present in lab so that you can shine some light on these and see if you do indeed have a precipitate. If the light passes through, that implies no precipitate. If they're scattering and the light sort of diffused and reflected out of the fluid, then that means there is indeed a precipitate. So now seems like a good time to end part 2 of the video. The video will be continued in part 3.